Hello everybody. Today we're going to learn about a new theorem that's going to help us compute line integrals in certain cases. So in the previous sections you learned a bunch of different ways to compute line integrals, and some of them were pretty tedious. You had to parameterize curves and it was a lot of work. And then you learned about conservative vector fields, and you learned about the fundamental theorem of line integrals that applied in certain situations for particular vector fields, and that made your life a lot easier to compute line integrals. Today we are going to look at yet another situation at certain conditions where Green's theorem applies, and that allows you to compute line integrals yet in a much easier way than by parameterizing. So let's look at Green's theorem. Let's read it together and see if we can figure out what this says. So Green's theorem, Green's theorem says, suppose C is a piecewise, smooth, simple closed curve that is a boundary of an open region R in the plane, oriented so that the region is on the left as we move around the curve. And suppose that the vector field f equal f1i plus f2j is a smooth vector field on an open region containing R and C. If all of those conditions are met, then the line integral over C of f dr is equal to the double integral over the region R of partial f2 partial x minus partial f1 partial y dA. That's a lot. So let's look at the diagram over here on the left to explain a little bit what has to be true about the curve in our line integral so that we can use Green's theorem. So C right here is a simple closed curve. That means that it doesn't cross itself. That's really all that we are saying. So if you have a curve that doesn't cross itself, and it's a boundary of an open region in the plane, oriented so that you are moving, as you're moving around this way, the region is on your left-hand side. So if that's the case, then our curve is so that we can use Green's theorem. Then the second condition that we are talking about talks about what has to be true about the vector field. The vector field is described as smooth. And smooth just means that you can take the partial derivatives and those partial derivatives are continuous. So they behave nice. There are no zeros in denominators. There are no points where our partial derivatives are undefined or discontinuous. So that's what has to be true about the vector field. It has to be nice and the partial derivatives have to be nice. And if that is the case, then we have this nice result that the line integral on the left can be replaced with hopefully a nicer double integral that's on the right. So on the right here we have a double integral. And in our formula it may not look nicer, but when you are, for specific cases, when you are computing those partial derivatives and look at the region you're integrating over, hopefully it's a nice region, and so your double integral is easier to compute. So that's what that note number 1 says. So the purpose of Green's theorem is to replace a possibly tedious line integral with a hopefully easier double integral. Those are the cases when you should look to use Green's theorem. Of course, we already talked about all the conditions that have to be met so that Green's theorem applies, and so it only applies to line integrals in 2 space, in the xy plane. So we don't have it in 3 space if our curve lives in 3 space, and it also only applies if our curve is closed. So just as in our picture right here, it's closed, right? So it's, if we have something that starts somewhere and ends somewhere else, we can't use it. If it's something that has a hole, we can't use it. So it really has to be around a closed curve. And then I already talked about what it means, what has to be true about our vector field. So the vector field has to be nice everywhere in the region, not just on the boundary. It has to be nice everywhere. So in particular, f1 and f2 must have continuous derivatives on that entire region. So no zeros in denominators, nothing strange like that happening. Okay, so this is the introduction to Green's theorem. Hopefully the statement makes sense. And in the next video, you're going to see an example for exercise 1, where we're going to apply Green's theorem. And then exercise 2, you should do, and then you can read the solution. And exercise 3, you can look at it. It's actually a case where Green's theorem doesn't apply, so it's a little bit a cautionary tale of what can go wrong in some situations.